Convex programs for CES exchange economies, demand of CES consumers, restored by characterizing the demand function of traders with CES utility functions. Consider a setting where trader I has an initial endowment, Wi equals to Wi1, Wi2 until Win in R plus to the end of goods, and the CES utility function, Ui of xi1, xi2 until xin equals to the summations of alpha ij times xij to the rho I, summing with index j starting from 1 to n to the term 1 over rho I, where alpha ij is greater than 0, wij is greater than 0, and rho I is between 1 and minus infinity, the negative infinity, but rho I is not equal to 0. If rho I is less than 0, we define ui of xi1, xi2 under xin equals to 0. If there is a j such that xij is equal to 0, note that this ensures that ui is continuous over r plus to the n. The demand vector for the ith consumer is unique and is given by the expression xij of pi equals to alpha ij to the 1 over 1 minus rho I over pi j to the 1 over 1 minus rho I times the ratio between the summations of pi k times wik summing for ok and the summations of alpha k to the 1 over 1 minus rho I times pi k to the minus rho I over 1 minus rho I summing for ok. The formula above can be derived using the Karush-Cohen-Tucker conditions. Efficient computation by convex programming. Consider an economy in which each trader I has a CES utility function with minus 1 less than equals to rho I less than 0. We show that the equilibria of such an economy can be characterized as the solutions of a convex feasibility problem, since the demand of every trader is well defined and unique at any price. We may write the equilibria as the set pi in R++, such that for each good j we have, the summations of xij of pi summing for oi is less than equals to the summations of wij summing for oi. Let rho equals to minus 1, and note that rho is less than equals to rho I for each I. Let fij of pi equals to pi j to the 1 over 1 minus rho times xij of pi, and sigma j equals to pi j to the 1 over 1 minus rho. In terms of the sigma j's, we obtain the set of sigma equals to sigma 1, sigma 2, sigma 3 until sigma n in R++, such that for each good j, the summations of fij of sigma summing for oi is less than equals to sigma j times the summations of wij summing for oi. We now show that these inequalities give rise to a convex feasibility program. Since the right-hand side of each inequality is a linear function, it suffices to argue that the left-hand side is a convex function. The latter claim is established by the following proposition. Proposition 6.11. The function fij of sigma is a convex function over R++. Proof. Clearly, it suffices to show that the constraint fij, which is less than or equals to t, defines a convex set for positive t. Using formula 6.7 for the demand, this constraint can be written as alpha ij to the 1 over 1 minus rho I over sigma j to the rho I minus rho over 1 minus rho I times the ratio between the summations of sigma k to the 1 minus rho times wik summing for ok over the term the summations of alpha ik to the 1 over 1 minus rho I times sigma k to the minus rho I times 1 minus rho over 1 minus rho I summing for ok. So the multiplications of these two terms is less than or equals to t. Rewriting and raising both sides to the power 1 over 1 minus rho, we obtain alpha ij to the 1 over 1 minus rho times 1 minus rho I multiplied by the term summation of sigma k to the 1 minus rho times wik summing for all k. The results of such a summation is to the exponent 1 over 1 minus rho, which is less than or equals to 2t to the 1 over 1 minus rho times sigma j to the rho I minus rho over 1 minus rho I times 1 minus rho times vi to the minus rho I over 1 minus rho I, where vi is equals to the summations of alpha ij to the exponent 1 over 1 minus rho I times sigma k to the minus rho I times 1 minus rho over 1 minus rho I, summing for all k. The results of the summations to the exponent 1 minus rho I over minus rho I times 1 minus rho, we set vi to such a value. The left-hand side of the inequality 6.8 is a convex function, and the right-hand side is a concave function that is non-decreasing in each argument when viewed as a function of t, sigma j, and vi, since the exponents are non-negative and add up to 1. Since 0 is less than minus rho I times 1 minus rho over 1 minus rho I, the term in the exponent of the vi, which is also less than or equals to 1, the right-hand side of equality 6.9 is a concave function. In fact, a CES function. It follows that the right-hand side of inequality 6.8 remains a concave function when vi is replaced by the right-hand side of equality 6.9. This completes the proof. It is not hard to verify that the demand generated by an economy with CES utilities as above need not satisfy WGS. Indeed, the connectedness of the equilibria that is a corollary of the above convex feasibility formulation is an interesting new consequence.